We now move our focus to the topic of electrolytes, a very important topic in chemistry and in reactions, and also very important for many physiological processes as well. Whenever we have an ionic compound and we put it into water and it dissolves, like for example we saw with potassium permanganate in the last part, it not only dissolves, it dissociates, which means it breaks up into separate ions, a positive ion and a negative ion, or multiple ions, many positive, many negative, depending on the formula. So we find that all of the soluble ionic compounds completely dissociate into those ions until the solution can no longer take any more of the compound in it. It is saturated. Whenever a solution contains ions, that solution is capable of conducting an electric current. In other words, if I attached two separate sides of a wire to a battery or an electric socket, much more dangerous, so I don't recommend doing that under most circumstances, and then I were to put those wires into a solution that contained ions, electricity would go right between those two wires. The more ions there are, the better it's able to conduct electricity. And so what we say is that those are electrolytes when we describe those ions, and we call that solution an electrolytic solution. And we can test for the presence of ions using a special apparatus, which is much like I described a second ago. It has essentially exposed electrodes, and those exposed electrodes are attached to a light bulb, and then that whole apparatus can either be attached to a battery or it can be plugged into a light socket. In the example we're going to see in this part of the lab, it's actually plugged into a light socket. And then we go ahead and immerse those electrodes into our solution that we want to test. So if there are ions, they act like a bridge for electrons, or if you think about this, electricity, to flow from one side of the electrode to the other. And as I said a second ago, the more ions we have in the solution, the brighter that light bulb will glow until it reaches a certain maximum. Now, a solution which contains a soluble ionic compound will be very rich in ions. There will be many ions. And we call such a compound a strong electrolyte. And we would call the solution itself a strong electrolyte solution. If a solution contains a compound which only slightly ionizes, so for example, let's say for every 100 molecules, only one of those 100 actually breaks up into ions, we would call such a compound a weak electrolyte. It technically still does produce ions. It will still conduct electricity, but what we would see with a light bulb in the example is that it's going to be much dimmer than we would expect for a strong electrolyte. And finally, non-ionic compounds do not break up into ions in most cases. And without ions being present, the solution cannot conduct an electric current. So as you might imagine, in our light bulb test that we described a second ago, we would see the light bulb remain completely dim. It would be unaffected when a solution is put between the two electrodes. Now, if we go ahead and take a look then at, for example, a compound like sodium nitrate, it is a soluble ionic compound. It is therefore a strong electrolyte. When I put it into solution, I dissolve it. It's better to describe sodium nitrate, for example, as a mix of sodium ions and nitrate ions separate from one another, rather than just writing it as sodium nitrate. When we have something like a non-electrolyte, or even weak electrolytes, what we do is we do not break them down. We do not dissociate them in equations, but keep them together. So methyl alcohol, also called methanol, has this formula here, CH3OH. We'll be talking about that quite a bit in one of the later chapters of the class, the compound methanol right there. And so in an equation, it should always be shown as its formula and not broken down into separate ions, because when you put it into water, it doesn't make those ions. It stays intact. If we look at figure 8.1, from your lab manual, this is going to give you a preview of what you would expect to see in this experiment. So this didn't print out very well, or didn't scan very well, as it were, but it gives a good enough representation. On the left, what we see is a strong electrolyte, sodium chloride. Sodium and chloride completely dissociate into ions in solution, and what we would find is when we hook this up to our light bulb apparatus, electricity is able to flow between the two ions here, between the two electrodes here, and our separate ions is trying to illustrate that it could act like a bridge. The picture doesn't really show the bridging part, but just understand that if you see a lot of ions, that means it should conduct electricity well. Let's skip to the extreme right, and let's say we have a non-electrolyte like sucrose. You'll notice that it does not break down at all into ions. We see absolutely no ions, and we would therefore expect our light bulb to remain completely dim when you put a sucrose solution into contact with those electrodes. So completely dim light bulb. The weak electrolyte, let's take a look at the picture here very closely. We're looking here at hydrogen fluoride, also called hydrofluoric acid in water. Look at the molecules, as it were. We have a molecule here, a molecule here, a molecule here, and another molecule here. Only one of these has been shown to dissociate, so there's very few ions compared to molecules. So will it conduct an electric current? Just barely. And the picture here is trying to show that the light bulb is conducting kind of dimly. But it still does conduct somewhat because there are some ions. That is a weak electrolyte. Some of the questions for this particular lab ask you to represent the electrolytes in equations, and so we're just going to take a quick look at how they want us to do that. So it depends on the type of electrolyte that we're going to have. Off to the left here, what I'm going to do is I'm going to look at generic equations using, for example, letters like X and Y to stand for cations and anions. So let's take a look at the strong electrolyte case first. So let's say we put a ionic compound, for example, into water, and we let it sit there. That will break into ions. It will dissociate. So the way we illustrate this is a regular arrow, and then the ions being separated out. For an example, consider nitric acid. Nitric acid is what we're going to call a strong acid. We'll discuss strong acids a little bit more later in the course. It is a strong electrolyte, meaning that the ions in it separate out. So again, notice that you have a regular arrow pointing to the right here, and you have the two ions separated out. With a weak electrolyte, you'll notice it's essentially the same format here, except we're using these double-sided arrows. What that kind of indicates is that the process is reversible. So the compound can break into ions, those ions can come back into the intact molecule. So an example would be a weak acid called nitrous acid. You'll notice the difference here is being the 3 oxygens in this compound versus 2 oxygens in nitrous acid. It is a weak electrolyte, meaning it only partially breaks down, and the way we indicate that again is with the double-sided arrow. Finally, non-electrolytes. There isn't necessarily a universal way of representing what non-electrolytes should look like. If we start off with an aqueous solution and the compound does not dissociate, we just write again a regular arrow towards pretty much exactly the same thing on the right side. Now, the one thing that can vary is the state. So, for example, on the left, maybe we're starting with a liquid A, but it forms a solution of aqueous A when it's added to water. Or it might be a gas, it might be a solid, but ultimately the important thing is it's written as the same way. There's no ions shown on either side, and we're just using, again, a regular arrow. The only time we used that double-sided arrow was with our weak electrolyte. So, here's an example. If I take chlorine gas and I bubble that gas into water, meaning I attach a hose to the gas container and let those bubbles go into water, the bubbles will dissolve to make chlorine water. And so I have shown that the state is different, but the most important thing to note is, again, it's just the same formula on either side. So an overview of what you're going to see in Part B. So we're going to test various solutions, and we're going to look for ions using an electric bulb apparatus. Strong electrolytes, as we said, completely separate into ions. So with strong electrolytes, we'll expect to see a bright light bulb telling us that this solution contains a lot of ions and it's a strong electrolyte. With a solution of a weak electrolyte, we are going to have some ions in solution, but probably not many. This is going to vary a lot from one compound to another, how many ions there actually are. But what we would expect is, since there's very few ions, the bulb will glow dimly. What does dimly mean? As I said, that can vary over a wide range, but let's just say not nearly as brightly as the strong electrolyte. And finally, non-electrolytes do not break up. They remain molecules that are neutral. And so when we go ahead and test this, we will see the bulb will not glow. As you watch this part of the lab, simply record your observations, and then you will answer the questions based on the results from those observations. Here are the solutions that we are going to test, and I will be testing them in the order that they are listed in the lab manual. And here is the electrolyte apparatus itself, currently unplugged. I will commence the testing by plugging in the apparatus. You will notice the two electrodes right there. There's air between them, so no electric current is currently being conducted. There's the electrodes. Notice I'm not touching those electrodes with those metal tongs, or I might be dead after the process, because those are very much live. All right, so the first solution I'm going to look at here is sodium chloride. And you'll notice when I take sodium chloride and test it, the bulb glows very brightly. Now I have to rinse off those electrodes with deionized water between each test to make sure that no ions remain on the electrodes before I go to the next test. Here we have the sucrose solution. Let's see what happens when we test that. Nothing seems to happen, even when I shake. So the bulb does not change its brightness at all. How about hydrochloric acid? Notice the bulb glows very brightly. Incidentally, I'm not showing the cleaning steps in the video right now, but these are being cleaned in between. Here is acetic acid. And you'll notice that the bulb does glow just a little bit. Here is sodium hydroxide. Again, the bulb glows very, very brightly. This is ammonium hydroxide. It's probably the trickiest one to test. Watch the center of the bulb very, very carefully. And if you see, there might be a little line suddenly pop up inside the bulb, like right there, I think it happened, and then disappears. So you might have to take my word for it on this, but it is glowing very, very dimly. Let's take a closer look. And right now we're putting the solution just under it. And if you look just about 2/3 of the way down, you might see a little bit of glowing fragment, but it's very, very hard to make out. But you just have to take my word for it. There is a slight glow right there. Now to ethanol. This is essentially a diluted vodka solution right here. And nothing. The bulb does not glow any brighter than it was when there was just air in between. Now, although it's not on the report sheet, let's take a look at what happens when we test deionized water and tap water. You'll notice that pure deionized water does not conduct an electric current at all. Tap water, on the other hand, you'll recall, has various ions dissolved in it. And so it does glow very, very weakly. Some of the ions in there would include some calcium ion and magnesium ion, and chloride and fluoride. Also not shown on the report sheet, but we're just going to test out here, is some Perrier mineral water. Notice that mineral water glows not too dimly, but it is still dim compared to what we would expect for a strong electrolyte. And finally here, we're going to take a look at a Gatorade solution. You'll recall that Gatorade is sold as containing lots of electrolytes for you. And if we go ahead and test that, again, that's not as bright as the strong electrolytes were, but it is still fairly bright. So I would consider Gatorade to be mostly a weak electrolyte.